We just understood about velocity profile. So let's use that to understand different cases. So I'll not read through this. Better would be for me to use it and explain it off. Okay, guys. So we have velocity profile of a non-viscous flow. I'll take a case wherein the pipe has no friction. Pipe has no friction. Okay. So I'll start with that, or no, actually I want to start the other way around. No, I'll start the other way around. Non-viscous, everything is non-viscous, my bad. This is supposed to be viscous. And yeah. Okay, so this is supposed to be viscous, but yep. Okay, let me start with this. So we have a pipe. So this is how we can represent a pipe. So we have a pipe which has friction. Okay. So basically, if I zoom in this, if I happen to zoom in, what we'll end up seeing is a surface which has things like this, right? Which is not smooth basically. So that's what will cause friction over here. And if we have a particle and if it's moving, say over here, so it will encounter friction because it's viscous within itself. But when it's moving on the edges, what happens? They bump around, and they might even get stuck. There's a possibility, right? So next thing will go here, say it is going, and it can get stuck over there. So next thing goes over there and it can get stuck over there. And next thing goes like this and it can get stuck over there, and so on and so forth. Next thing can go like this and it can escape and it might flow in this manner, right? So all of those are possibilities. So we are looking at viscous flow. So what happens over here is the particles can get stuck over there, and because it's viscous, there is friction, and the next particle might go, but because it has to brush across the one which is already stuck, what happens? This new particle will slow down. Does it make sense? Because this is slowing down, right? It's not actually at rest per se, it's not stuck, but it is slowing down. It will have a slowing down effect for the next particle also, but the thing is, the effect will be not so much. It will not resist that much basically, right? So on and so forth. Each layer this happens, there is some kind of slowing down as an effect, right? You have, say, particles which might look something like this. So I have a small video for that actually. Not very happy with it, but I think you guys be the judge. Right? Again, these are all the possibilities. It's not come out well. So I didn't get time to work on it exactly how I wanted, but yeah. So this is a possibility, So you have particles which are, few of them are stuck and few of them are moving very slowly, and you might end up in this way. Okay, so basically if I happen to take a cross section at a particular, say, place, right? And if I happen to talk to the molecules over here, right? Again, ask them about their velocity. They will tell their velocity. Of course, the ones which are stuck, they'll tell, well, I'm stuck. So my velocity is 0. My magnitude is 0. So end of it, we will have a velocity profile which might look something like this. This is a possibility. Okay, so by chance, maybe this side it has some velocity, and while this end, it might be this. So remember, this pipe is with friction. So we're looking at laminar flow. Okay. So we are looking at case, actually the very specific case that we are consider. This is a case of laminar flow. So for a laminar flow, the velocity profile in a normal pipe can look like this. Okay, so let me actually streamline this a bit. Discussion has to be proper. This you guys already know, we have already discussed. Say we enter and we ask. So this is a case of laminar flow. So in case of turbulent flow, I'll make space for that as well. We'll see what happens. So we have case of laminar flow. And the pipes are, so here the pipes are with friction, okay? So they have bumps and all of that, but it's non-viscous. So here, if I happen to zoom in, so there is bumps and everything. And the second thing that we need to be aware of is that there are bumps. Pipe has friction. Again, I'm just trying to expose to you guys what is laminar or velocity profile. So if I happen to cut the pipe over here and talk to the particles over here, right? I stop them and I go inside and ask them. I freeze the time, and for them I will unfreeze and everything else is frozen per se. They are not able to move, and I ask their velocity. The thing is, because of the friction, some of the particles on the edges, they will end up with zero velocity, while others need not. So basically, my velocity profile might look something like this. This is an hypothetical situation. This can be my non-zero velocity. This is our velocity profile. So this is clearly a non-zero velocity. So this is clearly non-zero velocity, and this is clearly a zero velocity. Okay, so again, what is that we are doing? We are actually plotting along your, in this case, y-axis per se, it's your radius, and here we are plotting velocity. So that's how we get velocity profile over here. Here too, against the radius, we're plotting the velocity. So that's what we are doing. If I put it across as a traditional graph, right, I can also showcase it like this, provided the pipe is up straight. So don't get confused. So if the pipe is up straight, if the pipe is up straight, the radius will be along the x-axis and the velocity is plotted along the y-axis. I take a cross section, right? I talk to these particles, and I might end up with a parabola like this. Okay, so I hope you are understanding what we are doing. So I'm talking to the particles, I'm asking their velocity, and I'm just plotting. Okay, he told at this position, right? If this is 0 for me, right, along the line, it's supposed to be 3-dimensional, honestly. But yeah, if I take this as the line, this is the radius, and from here to here, this end, say this is of 5 centimeter diameter. So this is your radius, 2.5. So exactly at the center, we'll have the highest velocity. Actually, it won't be flattened like that. It would be something like this. Straight up. This would be the case. Okay. So over here, what happens? Because on the edges, you have the velocity to be 0. Everywhere else, that is in between, the velocity is non-zero. So this is a case wherein we have laminar flow and we have non-viscous flow. So we are looking at a fluid which has no internal friction. So this means there's no. Sorry, I'm trying to make you guys get used to the words. So that's why I'm kind of dragging the discussion. So please don't mind. No internal. Actually, I don't have to be polite. You should. It just came out. No internal friction. You guys should know. There's nothing to be sorry about, actually. So this is a scenario, a weird scenario, of course, hypothetical. So here I'm taking a case wherein the pipe has no internal friction. Okay. And this is non-viscous also. So what happens? So if I happen to talk to the particles over here, right? And if I happen to plot, it would be a line like this. Again, there are actually different scenarios over here, but I'm not going to dive into it. I'm trying to keep it simple. So all of them will have the same velocity. All will have same velocity. Okay. Again, we're just getting used to all of this. So some of it might feel that it's out of syllabus, but again, to understand a concept, having different perspective helps. So that would be your velocity profile. So I missed out one case. What if it's turbulent? All this were laminar. Oh yeah, did I write? They are laminar. Yeah, laminar flow. Obviously here too it's laminar. So now we have turbulent. So case turbulent. Now in turbulent, if I happen to make them stop over there, and if I talk to them and all of that, same thing, same funda. The graph, it looks something like this, guys. It would look something like this, and it will flatten over here, and this would be the case. So velocity profile when you have turbulent flow. So now, why is this flat? Because we take the average. Because it is varying so much, the velocity is varying so much. So this guy tells I am almost at 1 meter per second. The next guy tells I am at 10 meter per second. The next guy might tell I am at 4 meter per second. Next guy can tell 20 meter per second. So it's at every second, it's changing very fast. It's turbulent, right? So your velocity profile will look like this. Again, we are plotting radius versus velocity. Just flip the pipe upside down, then the graph will make more sense. It's more relatable, that's what I mean. So this would be your velocity profile, right? It flattens. We take the average. So the line is flat because we are taking the average. It's like a plateau. The line plateau, right? Plateau is flat because we can only consider the average. Why should we only consider the average? Because it's turbulent. So that reasoning you guys can continue. Okay. Right. So I hope you guys got a good idea about velocity profiling and your viscous and non-viscous and turbulent and laminar flow. Again, don't study anything under one heading. Try to interconnect all the things that you're learning. Only then it makes sense. This, by the way, is an example.